good morning. I wanted to talk about disaggregated, sort of decentralized distributed storage from a very network-centric view. I'm obviously working in the networking space lately, so this talk is mostly about the networking element of this, and then I'll get back to the storage element a little later. And what's happening in the network, as you know, the world has moved to the cloud. There's billions of these and billions of tablets being served by millions and millions of servers in the cloud. You've seen the pictures. These are some pictures from the Google data centers. The size of football fields. They give employee bicycles, to get from one side to the other. That was on the consumer side. On the business side, lots of people moving to the cloud. It's estimated that by 25, roughly half of the enterprise workloads will be in the cloud. It's growing at about 20% a year, according to both Gartner and IDC. And obviously the cloud business itself, the search, social, and so on, is also growing at about 20% a year, driving tremendous hardware investment. The hardware side of this has dipped a little bit because, quite frankly, the hardware got cheaper. In particular, flash and memory got a lot cheaper in the last year or two. So people are getting more equipment for the money, but there's no question that by now over half the new servers are going in cloud environments, no longer on enterprise on-premise. And obviously the data center network, the business I'm in, follows that. So the majority of data center networking is now in cloud data centers. And one thing about these cloud data centers is that there's a lot of bandwidth within the data center, meaning the intra-data center traffic has grown the fastest. On the picture on the upper left, which is from Facebook, the little green slice on the bottom is the traffic that comes out of the data center. The red portion is what's going on inside. And this is being driven, of all things, largely by flash and distributed storage. So, and of course, new applications like AI, machine learning, video streaming, and so on. So the age-old question in the cloud was, you got 100,000 of servers, millions of virtual machines. How do you interconnect these things? And at a speed of tens of gigabits per second per server, which adds up to multiple petabits of aggregate no-logging bandwidth at microsecond speed. And the whole point of this is to make this cloud sort of transparent to the application so that the application writers don't have to worry about data placement. In other words, the application should be able to run anywhere with any amount of data, scale up and down as needed. In the old days, more than 10 years ago, before there was big enough network switches, people had these things called pods, not to be confused with iPods, but they were like clusters of maybe 64 racks that were interconnected with a switch that could handle 64 racks. But what people found out is it just didn't scale beyond the pod. And the new picture that is universally adopted now is leaf-spine networks, including multiple tiers of these, where you have basically equal distance between any server and any other server, meaning you can get to any data at the same speed. In a larger data center, like this is a picture from Microsoft, there are typically three, in some cases 4 tiers within the data center, and then they're connected through external gateways to yet other data centers in the same metro to build these metro redundant kind of aggregated data centers. And the same picture at Facebook, they showed it in a different way, but these 3 dimensions are essentially the 3 tiers of a leaf-spine network. These things are being upgraded in speed. So there's a steady march from 10 gigabit 10 years ago to 40 gigabit 5 years ago, 100 gigabit 3 years ago, and now emerging 400 gigabit. Incredible amount of ports going into this, about 15 million 100 gig ports this year, primarily going into the cloud. 400 gig is just entering the market. The projected volume for the next 4 years is 20 million ports. And these, of course, are 4 times the speed of the 100 gig port each. So this is the same sort of port transition in graphics here. 40 gig is still around, but declining. 100 gig took over very quickly, partially because the 100 gig price point was parity with 40 gig. So there was no economic reason to buy a 40 gig port when 100 gig became available. The 400 gig, which is starting to ship now, is about twice the cost per port of 100 gig. So it's cheaper on a cost per bit basis, but the optics are still fairly expensive. So it will take a little longer to ramp, but nevertheless, because it's 4 times the speed of a 100 gig port, it's projected to cross over the 100 gig shipment bandwidth by the end of Actually, this is funny shown by the end of 21, not 2020 here. And again, the majority of these 400 gig ports are expected to go into cloud. So the whole thing about these Ethernet speed transitions has been both, there was a demand side, people wanted of course more bandwidth, but it also was driven by reducing the cost of these Ethernet ports. And what's happening there in the cloud, I'm not sure you remember this, the concept of learning curves where new technology comes out at a stratospheric price point and then it takes years and years to get cheaper until people can actually deploy it. Well, that does not work in the cloud. In the cloud, nobody would buy a new technology that's more expensive than an existing technology. So for 400 gig to get any traction, it has to be cheaper, at least per bit, than the technology it will substitute, which is 100 gig. And of course, the cheaper it is, the faster the substitution happens. And if you don't get to volume, the old investment people making the silicon is not going to pay off. In the case of the 40 to 100 gig transition, the transition took about a year to the fifth percentile point, meaning in less than a year, the demand switched in the market from 40 to 100. The 400 gig ramp is a little slower. This is the latest forecast from Delora, which tracks this market. But it's still projected to go up very significantly starting later this year and the next many years. Now let me go down to the silicon a bit. You know all about Moore's law. This has been going on, of course, for the last 40 or more years, actually 50 years almost. This has translated on the network silicon level, the network switches, to a tremendous improvement. Every other year, these switches doubled in speed, essentially the same cost, which is a remarkable achievement. Now, part of this was that the network silicon was lagging in terms of process technology compared to CPUs and GPUs by a long shot. All the chips that were shipping until the latest generation that just got launched were actually 28 nanometer technology, something Intel shipped in 2011. The new chips coming out at 16, this is something Intel shipped in 2015. And it's only the generation after the current one, which is coming out next calendar year, which is at 7 nanometer, which sort of matches current CPU processes. Now, the advantage of that was the improvements were much more rapid. So in other words, as the technology shrank from 28, 16 and going on to 7 and 5, the number of transistors per chip, the number of buffers, table sizes on radically improved. So the net of this is that the new chips coming out are always better than the previous chip because they have more of the stuff that people want in a network. And of course, most importantly, they deliver more cost performance. And this has resulted in this dramatic, sort of cost reduction and size reduction where the biggest switch that I was involved in 12 years ago called the Magnum switch, which was a double wide rack with 3,456 ports at 16 gigabits each, 55 terabit capacity, is, as of this year, 2 1U boxes. So it's a very dramatic shift. Now, the negative of this is that the design costs for the silicon have gone through the roof. This is some estimates for Intel CPUs type chips. Networking chips are actually cheaper to design because a lot of cut and paste, like step and repeat. It's the same kind of structure repeated multiple times. Nevertheless, the tape-out cost in 7 nanometers, $10 million just for the mask set. Your CAD tool is going to run another at least $10 million a year. So by the time you have a team on this and get a chip out, you're looking at $50 million and counting, and it's probably going to be double of that in 5. And this only really works in volume, and the issue with that is you need, the industry isn't actually that large. So the combination of advanced IP, the demands driving to 7 and 5 nanometer transits to merchant silicon, which kind of has taken over the market. Most of the bandwidth shipping today is merchant silicon chips, primarily from Broadcom. There's also some other vendors. But the reason for that is that every year there was a chip following that Moore's law curve that doubled the speed or added more buffers or more routing and so on. And in terms of time to market, this just took over the market. Now there was this other element, which is the underlying SerDes speed, or the speed of the electrical lanes coming out of these chips. Until the current generation, everything was at 25 gigabits. So 100 gig Ethernet is actually 4 by 25. The new chips are at 50 gig SerDes, so 100 gig Ethernet is now 2 by 50. And the 400 gig Ethernet is 8 by 50. The next version of chips coming out next year will actually go to 100 gig SerDes, where 100 gig Ethernet is just 1 lane and a 400 gig Ethernet is 4 lanes, and you could actually build an 800 gig Ethernet in 8 lanes. Now, this has been key, of course, to get more throughput per chip because you're limited by I/O. It's also creating interesting dislocations in the market. So in terms of the projection on bandwidth, the 100 gig SerDes, which will show up shipping in any volume next calendar year, is actually now projected to be larger in terms of bandwidth by 22 than the entire market is this year. So the expectation is this will get adopted very, very rapidly. And the reason for that, of course, is it's cheaper. You get, with half the lanes per port, you get the same bandwidth. You can double the density per chip. You can double the throughput per chip. You can double the density per system, and so on. So we're in the midst of this transition, which it is a little hard to go. It's hard to go faster than 100 gigabit. People looking at 200 gig or 224 gig SerDes, but the physical reach on PC boards gets very, very short. So 100 gig will be around for a long time, and the issue with that is that you want to match the optics that connect to these electrical lanes in terms of the speed. The latest generation of optics is called 100 gig lambda optics, which is a direct match. Everything else requires gearboxes. So to explain that, the current optics, which are 4x25 matching the 25 gig speed, are still the highest in volume. In fact, the entire market essentially is 100 gig CLM4, 100 gig PSM4 optics. But going forward, 100 gig single laser optics, which is 100 gig DR, will be cheaper, and of course 400 gig DR4, FR4, LR4, all based on 100 gig lambda as well. So the good optics on this chart are the green ones. There's not too many 50 gig optics out there, so the current model of prediction is that there will be a massive transition from 25 gig lambda optics shown in green to the 100 gig optics shown in orange. And this sort of matches the form factors you're familiar with. There are, of course, ideas to take even an SFP module and run that at 100 gigabit. So you're not limited. SFP doesn't have to stay at 25 gig. It could go at 50 gig or eventually 100 gig. And the QSFP, which is 4 lanes, could go to 400 gig with 4 lanes of 100 gig. And the OSFP, which is an 8-lane module, will go to 800 gigs. So again, the majority of optics standards today are all based on 25 gig NRZ. The only one in the 100 gig era that's 100 gig lambda is 100 gig DR. In the 400 gig space, it's DR4, FR4, LR4, and in the 800 gig space, which hasn't been quite announced yet, but it's coming shortly, it's things like SR8, DR8, dual FR4, and FR8. There is talk about working on 800 gig Ethernet. In fact, some industry consortium is about to kick off to make that happen. It's actually very easy to make 800 gig Ethernet happen, which is you take the 400 gig spec and you change one number, which is the speed per lane. So this is one of the easiest standards to come to fruition. We hope to see this in silicon in a few years, but obviously there has to be a multi-vendor standard around it. It is harder to go faster. Part of that is that at 800 gig, the minimum packet size is 666 picosecond, which is 1.5 gigahertz. The internal clock rate on these chips tends to be 1.5 gigahertz. So with one pipeline, you can handle 800 gig. But if you wanted to go to 1600 gigabit Ethernet, you needed actually 2 parallel pipes, which means you don't get scalability at the silicon level in terms of cost. And the radix becomes too small as well. So the bottom line of all this SerDes and optical stuff is, 100 gig will be around for a long time. And anything else requires, gearboxes, either forward gearboxes or inverse gearboxes, which add significant cost and power. Now, switching over to the CPU and the PCI and the NIC side, PCI seems a little slow compared to what we just talked about. Almost all of PCI is still 3.0. The first CPUs with 4.0, of course, are announced and in fact shipping. But it came so late that a lot of people think that PCI 5.0 is around the corner. This is much needed both to drive faster I/O, to connect to more flash, and of course to have faster network interfaces. Dedicated GPU and specialized AI chips have even more need for I/O. So people there are looking at many times the throughput per chip than a conventional CPU. So they need even more I/O. And the sum of this is that we expect rapid adoption of 100 gig NICs for both conventional servers and for these AI GPU servers this year and next year. And just to showcase how where PCI has been, PCI 3.0 was actually launched officially in 2010, although I think the first systems shipped in 2011. That was 10 years ago. 8 gigabits per lane, 4.0 double stat, and 5.0 of course double stat again. But the key point here is with a conventional 8x adapter, today In PCI Gen 3 LAN, you were limited to essentially a dual 25 gig NIC, which is the industry standard for large cloud. With the 4.0, you can actually do a dual 50 gig or single channel 100 gig NIC. And with the 5.0, in 8 lanes, you can do a dual 100 gig. Or you could do 16 by PCI Gen 4 to do a dual 100 gig as well. So dual 100 gig is totally practical, or I should say economically justified going forward, because the underlying silicon cost isn't really any different than a dual 50 gig NIC. You just run the state machines a little faster. And if you look at this from the sort of rack level, top of rack level efficiency, the previous sort of top of rack chip that's still the highest volume today, called Tomahawk 1, which is a 3.2 terabit chip with 128 lanes of 25 gig. Typically, there's a 3-to-1 oversubscription going on to the rack level, which means you take 800 gig lanes going up, and you have the equivalent of 2400 gig lanes or 96 25 gig lanes going down, or it could be 48 50 gig connections to 48 servers in the rack. In other words, even today, in the last generation of silicon, you can connect every one of 48 servers on the rack with 50 gig, and there wouldn't be any point to go any less, because you're just wasting your money. You're straining the bandwidth. The new chip that's shipping now, called Tomahawk 3, has 4 times the bandwidth. So you can actually do 8 by 400 gig going up, and the equivalent of either 190 to 50 gig or 9600 gig servers going down. So the ability to interconnect a large number of servers at very high speed at very low cost is a given. And people typically use copper cable for these downlinks, I should mention, because it's the lowest cost. So we do expect people to upgrade from 25 gig and 50 gig today to 100 gig going forward. Now let me go back to the real topic that I wanted to talk about, which is how this matches to scalable distributed storage. So I mentioned earlier that the whole notion of disaggregating data placement from the application is absolutely key in the cloud, because you just don't know which thing scales and how much storage it needs and where all this data is. So the way to think about this is that the spine tier, the top tier of these networks, is essentially your total throughput of the whole data center, and this for a large data center can be in the petabit range. In fact, can be multiple petabits. And then all these servers underneath, which could be 10,000, 100,000 servers, connect through these spines to any other server in a few microseconds. I mean, the exact number is sort of depends how many layers you have, but it's perfectly fine for flash. So the point is, with the right storage architecture, you can actually disaggregate the applications from the storage completely. And quite frankly, this was always the goal. So this was, in the cloud, this was the goal for the last 10 years, because it does result in much better application availability, scalability, reliability. And the real question was how to do this without compromise, meaning data was getting bigger all the time, and there was a number of protocols, and there are a number of protocols in production that are doing this. So this is now getting to the more controversial part of this talk. So the largest installed base of this is arguably RoCE, or RDMA over Converged Ethernet. There have been 2 versions of RoCE, as you may know, the priority flow control, which relied on the network guaranteeing no packet drop to achieve good performance. The issue with packet drop is that a single packet drop requires you to redo an 8 megabyte transfer, and your performance goes pretty quickly to hell if you get any number of packet drops. Unfortunately, PFC doesn't really scale well into larger networks, so these applications that deploy PFC RoCE are limited to what we call cluster size, not entire data center size. They are in production. In fact, we provide the network for the vast majority of these, but it took a lot of fine-tuning to get this working. Now, the proponent of RoCE, which is primarily Mellanox, has a new version which uses early congestion notification to avoid the need for priority flow control. This is not yet in wide production, so I would say the jury is still out how will this scale, but obviously it would be preferable not to require PFC. And I should mention both of these now work over layer 3 technology. A very early version of RoCE did only work on a layer 2 network. Now the new kid on the block is NVMexpress over TCP/IP, which became a standard, I believe, a year ago, advocated by a company that's actually delivering a product here. Advantage of TCP/IP, of course, is it works beautifully on any SAS network. There's a reliable transport layer that guarantees that the packets arrive in order on the other side, and things get retransmitted if they drop in between. So we do believe this will be very robust and will be very easy to deploy. There is, of course, the overhead of driving the TCP protocol, which is primarily burdened on the server or the SmartNIC that implements this protocol on both sides of the equation. And people are looking at hardware implementations or highly dedicated, state machine kind of things to optimize the performance there. And then there are some other people in production that couldn't wait or didn't need to wait for the official NVMexpress over TCP standard that simply did their own version of a block storage protocol, which works in volume today in actually very large scale, but it's not published or standardized from that perspective. Now, the experience so far on all of this is that it does scale. The clusters with RoCE go to the thousands of nodes, and it's also clear that storage servers can saturate 100 gig links today. So this is with current technology. This could easily go up a factor of 2 or 4 in the future. A conventional server in these pictures can saturate at least 50 gig interfaces. So these are all sort of publicly reported numbers. And if they added more ports, they can probably get to 100 gig there as well. So getting 100 gigabit in and out of a server, current generation, seems quite feasible. What has also been emerged is that you don't want to run this anywhere close to maximum network utilization because both the latency and the congestions go up and packets drop. So the general advice is to keep network utilization below 50%, and this is the well-known sort of trade-off between latency and throughput, except in a network it's even worse than this theoretical curve. This is a queuing model because, again, the overhead of packet retransmission is very, very significant. Now, this can all be simulated. So there's work by a gentleman called Ariel Hendel and I think it's Lady Pallavi Shurpali at Facebook, which have built a NS3, which is an open source simulator for an entire data center network with, I think it was many hundreds of nodes, maybe thousands of nodes, multi-stage network, a queuing model for the NVMexpress, the storage layer, and so on. And what came out of the simulation is that, number one, the simulation results reasonably closely matched reality, which is a good thing. So what this means is one can experiment in the simulation model with settings on the exact protocol, data center TCP versus regular TCP and so on. But the main surprise to me was that just by making the network interfaces go faster, so you can in software dial in the speed of these interfaces, everything improved. So they actually dialed these things up, which they didn't have the hardware for, to a 200 gig Ethernet connection per server and on every link on the network. Even though the servers couldn't even nearly saturate this, but the overall performance improved, and the argument was you're sort of moving the knee of the curve on this latency chart to the right, which means, of course, that the network does perform better. So the long and short of this is, disaggregated storage, either the RoCE style or the NVMexpress over TCP style, works today at scale in large cloud networks. It did take a lot of tuning to get there, but it works. I think there's general agreement that TCP/IP or variants, like data center TCP, are by far the most robust transport layer. Although it's back to the performance equation, implementing that in either dedicated SmartNICs or state machines. And the promise of disaggregated storage that's robust and easy to use, meaning that anybody, mere mortals, could use this, is definitely here in the near future, meaning these same technologies will allow anyone to build an extremely arbitrarily scalable distributed disaggregated storage system on the network at whatever scale. And I was going a little fast here, but that was my slides. Thank you for my attention. If there's any questions I can answer, we have, I think, a couple of minutes. There's one, and you next.
Andy, many people have suggested that going to a two-tier network with central data centers and edge networks can alleviate some of these problems. And I think in the past you've been pretty skeptical of that. I'm wondering if you have changed your opinion.
Two layers, you mean like a leaf spine? Or?
Yeah.
Yeah, I mean, leaf spine with the switches getting bigger can support a tremendous number of servers, by the way. So, I mean, this picture is a simplified version, but with currently available equipment, you can, if I remember this correctly, you can go up to like 70,000 servers with just a leaf spine. So what is true is that the more layers you have, the more problems you tend to have. And one thing I forgot to mention on the simulation results is that one particular problem is downspeed conversion. So if the leaf spine runs at, say, 100 gigabit or going forward 400 gig, whereas the server connection is only at 25 gig, and that top of rack switch doesn't have a lot of buffering, you tend to end up with a lot of packet drops at that very point, because that's where the traffic sort of comes to a screeching halt before it trickles down in the server. And I think one reason that a network where all the links go 100 gig or faster works better is you have few of these speed conversion issues. So what is true here is that one should over-provision the network, and I'm not saying this in a self-serving way here, but it just works better, and you will have much fewer problems. And there was a question here.
Okay, so yes, it was a little fast, but just want to make sure I understand a basic concept. I think you said is that the device structures are sort of limited to support maybe 100 gigabit switching, and if you want to get to higher speeds, you have to do aggregation, and then the extra performance is basically a matter of the architecture over appropriate over provisioning and things of that sort. Is that generally correct?
Yeah, meaning, you know, the real question on the edge is how fast does the TCP, is it multi-threaded? Do you have a smart NIC? You know, the RDMA of course goes faster than the TCP version. And do you have multiple NICs? I mean, people are doing all kinds of stuff to get the performance up. But what is being deployed today in high volume is a dual by 25 gig NIC, and people have gotten 25 to 50 gig out of these things. And typically these servers, I should have mentioned earlier, have a whole bunch of, you know, M2 flash memory sticks, maybe 4, maybe 8. Each one of these M2 devices can do like 2 gigabytes each. So there's plenty of capacity in terms of I/O inside the box in terms of the direct PCI interface that you could output, you know, easily 100 gigabits if the network stack provides that. So this is sort of the current match is, you know, fill up the box with flash sticks or flash devices and then connect it to the network. And then the storage and the cloud is distributed across all of these boxes, because obviously it is it's arbitrary large data. And the only place to put it is sort of all over, which also allows you the redundancy by the time you do the, you know, M+1 sort of replication. There's some more questions in the back, and there's one there. So yes, it's if the service would be faster, people would go faster, but it's limited by the throughput you can achieve on the server level.
Do you foresee some of these upcoming interfaces like CXL, Gen Z, impacting the networking architecture, and if so, how?
Yeah, that's a very good question. So there are, you always have to start with the application, right? So there are applications that will work much better, you know, in a large CXL, ultimate DRAM, I don't know how many terabytes of memory environment, like some database thing, where you have very tightly coupled, you know, interactions. What I was talking about is the conventional cloud, you know, search social environment, and the conventional enterprise as a service going into the cloud, where you take existing applications and just move them from on-premise into the cloud without changing the application model. But there's a whole separate opportunity how to take advantage of all this great new stuff coming in with, you know, persistent memory in the same huge box, could be a rack full of memory. And that may completely change what you can do there, but it's not going to change what Google and Facebook is doing in the cloud right now.
Sats here from VMware. My question is twofold. One is, you mentioned about when you move from 100 gig to 200 gig NIC, you see the improvement in performance. Can you quantify how would you do that? Like what kind of performance improvement you see it? And second part is, as we move from 100 gig to 200 gig on the NICs, on the servers, do you see a need for the NUMA-aware networking inside the servers? Thank you.
NUMA-aware networking, you mean like coherent? In NUMA, what do you mean by NUMA-aware within the network? So.
Basically talking about
Oh, yeah, the current trend is actually to fewer sockets for the simple reason that even going from one socket to two socket currently doesn't scale that well, as you may know. So people are filling up these CPUs with memory buses to get more memory bandwidth, and there just isn't enough, I don't know, pins left over to drive another socket at the same speed, right? So I would say, you know, 64 core chips where it may be multiple sockets in one device, but not sort of externally to get more interconnectivity is the future. It just gets a little hard to cool at some point. But going back to the networking speed, it's basically an economic trade-off, right? So you do pay by bandwidth, so higher bandwidth costs money, but you also gain a certain amount of performance. So what everybody in the cloud has been trying to figure out is what's the optimal spend, between the storage and the servers, the compute, which is the much bigger portion of their spending, compared to the network, which is a much smaller slice. You don't want to spend too little on the network because you would bottleneck the servers, but you also don't want to spend too much where it doesn't really improve the performance of the server. So until now, that trade-off was at the 25, 50 gig level per server, and typically 3-to-1 oversubscribed at the TOR, because you don't have all the servers being active at the same time and going into the storage, right? So that's just the universally accepted sort of design point today. But as CPUs will double in cores, the throughput will double. As the flash goes faster, the I/O goes faster. So it tracks the underlying technology in terms of both CPU cores and flash in predictably upping that speed. And I think I'll have to leave it at that. Thank you very much. All right.